Hello and welcome to the 20th session of the Introductory Biostatistics Distance Learning course. Today we're going to talk about how to do analyses of multiple 2x2 tables in stata, which was the topic for the last lecture. So you'll remember we started talking about one 2x2 table, and then we thought, what if there's a third variable or confounding factor, such as the site at which the data was collected or something else that could impact the association between the two binary variables that we're looking at. So what we did was we said, okay, if we have these multiple 2x2 tables, what we want to do first is think about, should we combine the information in the multiple 2x2 tables? In other words, is the strength of the association, the odds ratio, similar in each of the two 2x2 tables? So what we do is this test for homogeneity, and here I've written the null and alternative hypotheses for the test of homogeneity. So the null hypothesis is that the odds ratio in the first 2x2 table is equal to the odds ratio in the second, is equal to da-da-da-da-da, all the way up to the kth odds ratio, okay? And then the alternative, just like we saw in the case of analysis of variance, is that at least one of the odds ratios is different, okay? So today we're going to look at a new example using the SEPO dataset and think about how to apply this, what we've learned in lecture, how to conduct the tests using stata. Okay, so here's our test for homogeneity. Now we're going to think about this in terms of an example from the SEPO dataset. So let me switch over here to stata. I'm going to switch the example a bit. Remember, before we were looking at this variable death, CENS, which was whether the patient died on the study or not. Now I want to assess the relationship between that variable and whether or not the patient was diagnosed with pulmonary TB at baseline. Okay, so if I go to the variables window, you'll see that there's this variable here called pulmonary TB diagnosis, PULTB dx, which is whether or not the patient had pulmonary TB at baseline. Okay, so before you do any sort of analyses, it's always good to get a sense of the variables that you're working with. So since pulmonary TB at baseline is a binary variable, let's use the tabulate command to see how many people have this condition. Okay, and so you'll see the results here. Pulmonary TB at baseline, yes, there were 59 such patients, and 591 patients without pulmonary TB at baseline. Okay, so it looks like 9% of the patients had TB at baseline. Okay, and remember, the other variable we're interested in is whether the patient died on the study or not, which was death, CENS. So we can tabulate that variable as well. And it looks like out of the 650 patients, 37 of them died while the study was happening. Okay? All right. So now we might be interested in the relationship between, we might think that patients with pulmonary TB at baseline are more likely to die on the study than patients without pulmonary TB, okay? And so in that case, we might be interested in looking at the odds ratio, okay? All right, so if we were in the, if we were 2 lectures ago and we were just looking at this one 2x2 table, we might proceed as follows, okay? So we might say, so we would go to statistics, epidemiology and related, tables for epidemiologists, and then we might, for example, go to this case control odds ratio, okay? So I'm going to select that. All right, so my case variable is death CENS, and then my exposure variable, I'm just going to go down and choose pulmonary TB diagnosis, okay? And then from there, I will just hit OK. Okay, you see, it gives me results in a the results are not what I want, because everybody is in the exposed group and nobody's in the unexposed group. Remember, we talked about this in the last stata session. Because pulmonary TB at baseline is this yes-no variable, stata wants it as a 0-1 variable. Okay? So what I'm going to do is I'm going to generate a new variable which contains the same information but is just numeric. Okay? So I'm going to type in generate, and I'll just call it TB, which is the name of my new variable. So generate TB equals pulmonary TB diagnosis, the existing variable, -1. Okay? So now I have this new variable. Let me take a look at what that looks like. So I'll just type in tabulate TB, and there it is. And then I just want to compare it to the variable that I used to create it, which was pulmonary TB diagnosis, And you'll see that it's kind of confusing, because here in this new variable that we created, a 0 means yes. Okay? So there were 59 people with pulmonary TB at baseline, and those people are the zeros. Okay? Alright, so now if I use this new variable and I go to the same place I was before, statistics, epidemiology and related, tables for epidemiologists, case control odds ratio, and now for the exposure variable I choose TB, and I hit OK. Now it does what we're looking for it to do, okay? But now we just have to be very careful with our interpretation, okay? Because typically we would think the exposed would be those with TB, but because of the way the variable is coded, the exposed here are the people without pulmonary TB at baseline, okay? Meanwhile, the unexposed, the 59 unexposed, are the ones with TB, okay? And so you'll see the odds ratio is 0.61. The fact that it's less than 1 would seem to make sense, right? Because this odds ratio is the odds of the outcome for those exposed compared to the odds of the outcome for those unexposed. Okay? So this is telling me that the people who do not have pulmonary TB at baseline are less likely to die on the study than those with pulmonary TB at baseline. Okay? And so that makes sense. But you'll notice that the confidence interval is actually quite wide, from 0.22 to 2.11. And a large reason for that is that we only have 5 people with TB. I mean, we only had 59 people with TB in total. And 5 of those 59 ended up dying on the study. But that 5 represents a small sample size, right? And so that's why our confidence interval is so wide. And so that means we have a problem with power. We have very little power to detect a difference in rates of death on the study between those with TB at baseline and those without TB at baseline. Okay, and so you'll see we got this p-value which was greater than 0.05. So it's not so much that this means that there isn't a relationship between TB and dying on the study. Instead, it means that we have a lack of power. We have too few samples to be able to conclude that there is a significant relationship. Okay, so this is important to know. This is why, getting back to our first discussions of hypothesis testing, this is why we, when we have a p-value greater than 0.05, like we do here, we say that we fail to reject the null instead of saying that we accept it. Okay, that's why we say we fail to reject the null, because it might just be the case that we don't have enough samples, which appears to be the case here. Okay, so but the point estimate, this 0.61, makes sense. We're saying the odds of death are lower for those without TB than those with TB at baseline. Okay. Okay. So so just to take this example a little bit further, it kind of doesn't make sense, given that I've talked about having a small sample size of only 5 patients with TB that died. It sort of doesn't make sense to further break this down into multiple 2x2 tables, but just for the purposes of illustration, I'm going to do that. So in real life, we would hope to have more numbers in these cells, particularly this one, the 5, to think about multiple 2x2 tables, but just for purposes of illustration, so we can see what these things look like in stata, I am going to proceed in this way, okay? So now we're thinking about multiple 2x2 tables. In particular, I want to see whether this relationship between dying on the study or not and pulmonary TB at baseline, whether this relationship is affected by the gender of the patient at all, okay? And so let's tabulate. The variable that encodes gender is called sex. So if I tabulate sex, you'll see that we had many more women. It looks like almost 70% of our sample was women compared to only 30% men, okay? And you'll remember, because this variable sex has male-female, we had to generate a new variable, which we called sex2, to make it a 0, 1. So if I tabulate sex2, you'll see that 0 means male and 1 means female, okay? So we're going to need that going forward, okay? So basically what I'm looking at is, does the relationship between pulmonary TB at diagnosis and death on the study vary by gender? Okay, so that's the question that I'm trying to ask. And the place that I'm starting, you'll recall, is this test for homogeneity. Okay, so here in our specific example, what we're looking at is whether the odds ratio for women is equal to the odds ratio for men. And here, when we talk about the odds ratio, again, it's always important to be very explicit about what you're looking at. We're talking about the odds of death on the study, which is another way of saying death during the study, the odds of death on the study for those with TB versus those without TB. Okay, so that's what we're assessing here, and we're going to start off with this test of homogeneity to see whether gender impacts this relationship. So let's return to stata. So we just have an additional piece. So we're going to go to the same spot we went to before, which is statistics, epidemiology and related, tables for epidemiologists, case control odds ratio. And again, my case variable is this death, CENS, tells me whether a patient died on the study or not. My exposure variable is TB. And now in this menu, I'm going to select this option called, I'm going to select options, rather. And you'll see there's this option called stratify on variable. Okay, so I want to select that. And then, it's already filled in for me, but I want to stratify on this variable called sex2, which I've created, which is down here at the bottom. Okay. And so you'll see now that I've selected the stratify on variable command, I can select this use Mantel-Hansel for the weights. Okay, so that's very helpful because now I can think about whether we can combine the odds ratios for men and women. Okay, and so I'll also hit this Fisher's exact P, because you'll remember that we have a small cell. Okay. All right. So here are my results. Okay, and so it gives me if I look here, sex equals 0. That's males. Okay. So here's the odds ratio for males. Again, that's the odds ratio of death among those without TB compared to those with TB, and that's the reason why it's less than 1. Okay, And then again, here's the odds for women, comparing the odds of death in those without TB compared to the odds in those with TB. So you can see that the relationship looks very similar for both men and women, right? Because one's 0.56, one's 0.65. That looks like just sampling variability could explain that. But we can do a formal statistical test, which is this test for homogeneity, the Mantel-Hansel test, which is down here. Okay, so here's the chi-squared statistic, 0.02, and then the corresponding p-value, which is 0.88. Okay, so since our p-value is greater, much greater than 0.05, we fail to reject the null hypothesis. And in this case, if I can switch back here, we conclude that this seems reasonable. It seems reasonable to say that the odds ratio of death on the study for those without TB compared to those with TB is similar for men and women because of this result here from the Mantel-Hansel test of homogeneity. Okay? All right. So that's step one in what we've been discussing. Step one was this test of homogeneity. Okay? And since the test of homogeneity was not rejected, we can now combine the information in the multiple tables. In other words, we can combine the information for men and women in this example to yield a single summary measure of the strength of the association, the odds ratio. Okay? So now in our next step, we want to calculate the Mantel-Hansel odds ratio, which is here, the Mantel-Hansel combined. And so it looks like the odds ratio is 0.62, and here's the corresponding 95% confidence interval from 0.23 to 1.66. Okay? So if I can just summarize that information, I would say that I'll switch over here. We would say that our odds ratio for the Mantel-Hansel is 0.62. And again, you always want to be clear about what this is saying. We're looking at the odds of death on the study for those without TB compared to those with TB. Okay, so there's our relationship, and again, we don't stop there. We want to say, is this significantly different from 0? Okay, so if I'll switch over here again, so now that we've failed to reject the test of homogeneity, concluded that we could combine the information in the multiple tables, now we want to test this null hypothesis, which is that the Mantel-Hansel combined odds ratio is equal to 1. And obviously the alternative hypothesis will be that the Mantel-Hansel combined odds ratio is not equal to 1. Okay, so how do we do this? Well, it turns out we already have the stata output that we need to answer this question. And we could do it in several ways, just like we've seen before. We could look at the 95% confidence interval, and here we can see that the value 1 is contained within this confidence interval, so that we would conclude that yes, in fact, it appears that we would fail to reject the null. And we get the same output down here, the test that the combined odds ratio is equal to 1. We would fail to reject because we have this p-value of 0.339. 0.339 is greater than 0.05, and so as a result we would fail to reject the null and conclude that based on our sample, there does not appear to be a significant relationship between baseline TB and death on the study. Now again, that's why we always say based on our sample, right? The reason it makes sense to say it here, as always, is because we would really expect many more patients, with TB to die on the study than patients without TB. But the reason we weren't able to find a significant effect here, I think, has largely to do with the fact that we have a small sample size, which we mentioned before. Specifically, if we scroll back up, we only had 5 people with TB who died on the study, okay? And only 59 people with TB in total. So that might be what's driving this relationship. And so it may not be the case, it may be the case that there is a relationship between death and TB, but based on our sample, we weren't able to find one, okay? So those are the 3 steps that we go through when we have multiple 2x2 tables. So just to summarize, in step 1, we're trying to ask the question, should we combine the odds ratios? And so that's where we do this test of homogeneity, which asks the question, is odds ratio 1 equal to odds ratio 2 equal to all the way up to odds ratio k? And so we do that test of homogeneity first, and then, so if the test of homogeneity is not rejected, so if it's rejected, remember, what we conclude is that at least one of the odds ratios is different, and then we report separate odds ratios. Okay, we say here's the odds ratio for men and here's the odds ratio for women, for example. But if the test for homogeneity is not rejected, okay, then we combine the odds ratios. Okay, and this is where we use this thing called the Mantel-Hansel method. Okay, that's what we use to combine the information. The Mantel, I always have to think critically about how to spell this. The Mantel-Hansel method. Okay, and then once we have a combined odds ratio, so this gives us the odds ratio Mantel-Hansel, the combined. In step 3, we want to see, just like we would if we had only one 2x2 table, we want to see is, whoops, this is my null hypothesis. The odds ratio Mantel-Hansel is equal to 1, and obviously the alternative would be that the odds ratio, the combined Mantel-Hansel, is not equal to 1. Okay? Alright, so that's how we do that in stata, and I'll stop there and I will see you in the next session.